Hello. This is a video for chapter 4, and I think that I assume that you have watched the video on chapter 3 already, but if you haven't, you should. So this is on probability distributions, and I hope you're doing well. And let's start. So let me, as usual, turn my video off and go directly to chapter 4 PowerPoint. So this chapter is about discrete random variable and discrete probability distributions. So let's look at some examples. I'll let you read. These are just the sections that the chapter covers. So probability distribution function for a discrete random variable. What does that mean? So let me give you an example before I go through the chapter here. So if we flip a coin twice, you know the sample space would be these, of course, right? That's the sample space. Flip a coin twice. Now, from here, we can define a variable. We call it a random variable. And the random variable has numerical value. So we can define it to be, let's say, number of heads that we can get. What are the number of heads that we can get? Well, it could be either 0 heads when you do it twice. You get 0 heads, no heads. Or you can get 1 head, or you can get 2 heads. So the probability of 0 head would be, and I'm seeing that I'm missing TT. Let me fix that. Okay, this should be TT. We have HT and TH, HHTT. Okay, 0 head would be that one, so it's 1 out of 4. And the probability that you get 1 head would be 2 out of 4. 2 out of 4. And probability to get 2 heads is 1 out of 4. Now, this right here is called a probability distribution. And since the values of x are discrete, it's called a discrete probability distribution. And this variable is called a random variable. In this case, it's a discrete random variable. And notice that all the probabilities are between 1 and 0. And if you add them, see, 1/4 plus 2/4 plus 1/4 is 4/4, which is 1. And this is always the case for probability distributions. So again, we have a chance experiment with a sample space, and based on sample space, we define a variable and then find the probabilities of the values of that variable. Now, the way that we do this has to be a way that guarantees that the probabilities would add up to 1. Now, how do we guarantee that? We have to make sure we take every outcome into account. So that means we cannot make a probability distribution, if we don't count that one. If you do that, then the probabilities would not add up to 1. Now, what if we take that and then we define it in a way that counts one of these twice? If something is counted twice or more, then the probabilities would add up to a number greater than 1. So we know it's not a probability distribution. So probability distribution, the probabilities have to be between 0 and 1, and they have to add up to number 1. Okay, so now that's not the only random variable you can define. You can define, for example, random variable to be number of tails instead of heads. Okay, so that's those are the two conditions for a discrete probability distribution, that each probability is between 0 and 1 inclusive, and the sums add up to 1. So here's an example. A child psychologist is interested in the number of times a newborn baby is crying wakes its mother after midnight. So they took a sample, and they have values for x here. So it is a 0 time, 1 time, 2 times, 3 times, 4 times, 5 times the mother was the baby woke the mother. Okay, so now what are the probabilities? Well, the probabilities are given based on the data that they had. So 2 out of 50, they said 0 times, right? And then 11 out of 50 said 1, and so forth. So we have numbers and we have probabilities. Is this a probability distribution? Yes, because the probabilities are between 0 and 1, and they add up to 1. If you add them, you see, you get 1. All right, so why is this a discrete probability distribution? We just said, because the probabilities are all between 0 and 1, and they add up to 1. All right, what is the expected value? Well, expected value, going back to the example that I gave you, if you flip a coin twice, but these are going to be the outcomes. So if we define a random variable to be number of heads, right? And we said that this would be 1 over 4, 2 over 4, and 1 over 4, right? This is a discrete random variable, probability distribution. Now, if we take each probability and multiply it by the value of x and add them, so 0 times 1/4 plus 1 times 2 over 4 plus 2 times 1 over 4, what we're going to get is basically 0 plus 1/2 plus 1/2 is going to be what? So let me get rid of that. So that would be 0 plus, that's 1/2 plus, and this is also 1/2. So 1/2 plus 1/2 plus 0, that's 1. That's 1/2. So 1/2 plus 1/2 plus 0, that's 1. So they add up to 1. So these add up to 1. What does that mean? Well, that is something we call expected value of x, which is the same as the mean, right? And in this case, this is 1. What does that mean? That means if we do this experiment many times, so every time you flip two coins and see, let's say you do it one time and you flip 2 coins, you get 2 heads. Next time you do flip 2 coins, you get 1 head. Next time you get 0. Next time you get 2. Next time you get 1. Next time you get 0, and so forth. Now, if you do it many times, let's say 1,000 times, and add up all of these numbers, number of heads that you get, and so if you add them all up and then divide that number by 1,000, you will get approximately 1. That's what this means. So that is the expected value of this random variable. So the formula for it is given by this formula, which is not a surprise, because remember, if we have x and fi, which is the frequencies, let's say we have 1, 2, 3, and we have frequency, let's say 3, 2, and 1, right? 3, 2, and 2. So that means we have 3 1s, 2 2s, and let's make this 2 also, 2 3s, right? So we know the mu is going to be sigma xi, right, times fi divided by sigma fi. Sigma means sum, right? So that means you basically do 3 times 1 and then 2 times 2 and then 2 times 3 and then add them all up, which is the numerator. And then you add the frequencies and you get the denominator and you get mu. But in our case, what we have is not fi but is pi. So this is, let's say we have 1, 2, 3, and these are probabilities. Let's say probability of well, we can do the same example we just did. Let's do that one. So the number of heads is 0, 1, or 2, and we said this is 1/4, this is 2/4, and this is 1/4. Now, to find the mean, well, we have to do the same thing. We have to multiply xi by pi this time, and then divide by sum of pi's. But the pi's, the sum is 1, so we end up with this formula here. Now, the standard deviation is the same thing. To find the standard deviation, if we have x and fi, we're going to have to take each x, subtract the mu from it, and raise the second power and multiply by fi, and then divide by sigma fi. But the sigma, if it's instead of f we have p, then this would be 1 and this would be pi, and that's that formula right there. Okay, so that's where they come from. Okay, so to find a, we don't do it by hand, we use a calculator. So let's use a calculator. And so the way we do it is by going to stat, edit, and we need 2 columns, so we clean them up. We learned how to do that before. So you go to L1 and you put 0, 1, and 2. And in L2, put point. In this case, I'm going to do this one because this is about the soccer game, right? It says a men's soccer team plays soccer 0, 1, or 2 days a week. Now the probability that they're going to play 0 times is 20%. Probability that they play 1 time is 50%. And the probability that they play 2 times is 30%. And these are the numbers that are given in this table right here. You get my pen is there. So you see this table right here. Okay, so I'm going to put those numbers in there. 0.2. So I'm going to put point. Oops. So 0.2, 0.2, and then 0.5, and then 0.3. Okay, and then to find a mean and a standard deviation, we could just go to stat, calculate. One variable stat. We put L1, comma L2 there. And here you go. The mean is 1.1 and the standard deviation is 0.7. Now notice the standard deviation Sx is empty. Why is it empty? Well, because it's empty because remember the formula for a standard deviation if you use a sample is like that, right? And then you have to multiply by, pi, and then, fi if you have the frequencies, and then you have to divide by n minus 1. Now if you change this to pi, then we would have to divide by sigma pi, which is 1, minus 1 is a 0. Denominator cannot be 0 in mathematics. So that means the calculator cannot use the sample standard deviation formula. It has to use the population. And in fact, we don't want the calculator to find the sample standard deviation. We want to find the population, because these are all the values of x. So this is not a sample. All right, so that's why you don't see anything in S right here. Is empty. So standard deviation of this probability distribution is 0.7 and the mean is 1.1. The x bar is the same as mu, and the mu in this case same as expected value of x. All right, so again, it's another example. It says you're playing a game of chance in which 4 cards are drawn from a standard deck of cards, 52 cards. You guess the suit of each card before it is drawn. The cards are replaced in the deck, and then they take another card. So you pay $1 to play. If you guess the right suit every time, that means 4 times in a row, then you can win $256 and you get your money back. Okay, so that means the chance that you win is basically the chance that, what's the probability that you guess it first time correctly, and second one, and the third one, and the fourth one, the fourth time you do it. So the probability of that happening is this. Now, so what can you lose? Well, let's let x be how much money you're going to have after you play this game once. Well, you can lose $1. And what's the probability of losing $1? Well, we're going to calculate that. But you can also win $256. What's the probability of winning that? Is 0.0039. So that's the probability of winning, and that's the probability of losing. You have to subtract that from 1, right? And we get this number right here. So what's the expected value of this? Well, you can do the same thing I just did with the calculator and find the expected value, right? You put these in L1, you put these in L2, and go through the same process. You are going to end up with mu, or expected value, is equal to that. Or if you move the decimal 2 places to the right, you get it in terms of cents. So this expected value is positive. That means in the long run, you can actually win this much every time you play. But notice that this much is a really small amount. That's 23 over 100 of a penny. So it takes you a long time to actually win anything here, right? So this is a game that is actually in your favor. When the expected value is positive, it means that in the long run you can win whatever that number is per game. If the expected value is 0, it means you neither win nor lose, so it's a fair game. And if the expected value is negative, which is the case for most games played in casinos, that means for every play on average, every time you play, you lose whatever that number is. Let's say they charge you $2 to play, and the expected value of the game is $1, right? Negative. If it's negative $1 and they're charging you $2 to play, that means every time you play, you lose $1 of that. All right, so that's expected value. All right, one type of there are many different types of distributions. We're going to talk about 3 of them in this chapter. So first one is, these are the famous ones, celebrity distributions. So first time, it's very famous, is binomial distribution. In a binomial distribution, you have a situation where there are only two things, two outcomes that you're interested in: success or failure. For example, suppose let's say you flip a coin, right? Let's call the H success. So I say, what's the probability of success, right? That's 1/2. And then we call the other one failure. So in this situation, we have a binomial situation. Now, suppose we flip a coin 10 times, and we are interested in knowing X. How many successes can I get? That means when I flip a coin 10 times, how many out of 10 times, how many heads can I get? Well, you can get 0, you can get 1, you can get 2, all the way to what? To 10 successes. And each of them will have a probability. This kind of situation is a binomial probability distribution. So there is a probability of success, right? And then there is probability of failure, which is 1 minus probability of success. And then there is many tries that you do it, which is called n. And then you figure out what's the probability of each value of x. That's what this probability distribution is all about. So in this case, for example, Joe randomly guesses at a true-false stat question. So of course success is guessing it correctly. The failure is guessing it incorrectly. Suppose Joe always guesses correctly on any stat question, true-false question, with probability of 60%. So probability of success, the letter we use for it is P. And probability of failure is Q, which is 1 minus P. So in this case, probability of success 0.6, probability of failure is 0.4. This means for every true-false stat question Joe answers, his probability of success 60% and probability of failure is 40%. So this experiment is an example of a binomial experiment. Now, if you do it many, many times, maybe n times, then we have a probability distribution. So there are conditions that have to be satisfied for the probability distribution to be binomial. There are fixed number of tries, so you do it n times. There are only two possibilities. It doesn't have to be two outcomes, it's just two things you're interested in. For example, let's say you roll a die. There are 6 different things that can happen. But suppose we call this success and we call everything else failure. Then we have a binomial situation, even though we have more than 2 outcomes. So when we talk about binomial, we are talking about 2 things that you're interested in. One is success and one is failure. You define them what to be, what they are, but there are only 2 of them. All right, so and also the n trials have to be independent. For example, if you take a card out of the 52 cards, suppose you have 52 cards, if you take a card out of 52 cards, then if you don't put it back, next time you take a card, the probability of success changes. If the success is, let's say, getting a red card, for example. So that means in this situation, when you take cards from a 52 card deck of cards and you don't replace them, that situation is not binomial. Why? Because the n tries that you do, if you do it like 5 times, every time you do it, it changes the probability of the next card because you're not replacing it into the stack of cards. All right, so if these are satisfied, then we have a binomial distribution. Now, I have here in the notes, I derived the formula, where formula comes from. You should read it. In this course, we're going to use calculator to find the probabilities. But let me explain quickly where the formula comes from. We're not going to use the formula directly. We're going to use the calculator. So here there's knee surgery that has 75% chance of success, and the surgery is performed on 3 patients. Find the probability of the surgery being successful on exactly 2 patients. Now, first of all, here in this example, I'm going to do it. First of all, you know that you can easily figure out how many outcomes and in what combinations, right? If you do it 3 times, every time you do it, there's a probability of success and failure. So basically what we're going to have in the sample space is going to be all of that, right? You can get 3 successes, or you can get 2 successes but different ways, right? So these are all 2 successes different ways. And then you could get 1 success in different ways, and then you could get no success, of course, only one way. Only one way you could get 3 successes, only one way you can get 3 failures, but you can get 3 different ways you can get 1 success, and 3 different ways you can get 2 successes. Now, the calculations, I'm going to make a mistake here, and you caught my mistake, right? Can I say I'm interested in these 3 because they have 2 successes in them, and then divide by 8 because there are 8 of them? No. Why? Because these are not equally likely. They all have different probabilities. So I can't just count and then divide by 8. Doesn't work. So this is not correct. How do we do it? Well, we're going to have to find each of these probabilities by the product formula. Remember the multiplication formula? So we're going to have to multiply the probabilities of these to find out what they are, and then we have to add them. Add these 3. Because we want to success this way, or this way, or this way. Now, that is a lot of work. So people who try to do this first time, they realize this is a lot of work, especially if you do it like, let's say, 1,000 times. Then you can imagine what this table will look like if you do it 1,000 times. It's a big, huge mess here. So what they did, they looked for a pattern so they can find a formula for this, and they found it. So the pattern has to do with, so the question is how many different ways, and I'm going to give you the answer here, but we're not going to do it this way. You could find the answer because to get 2 successes and 1 failure, you have to multiply the probability of success, which is 0.75, and then, which is 3/4, right? So let me do it. So 3/4, and then times 3/4, and then times 1/4. So that's how you can find the probability of 2 successes and 1 failure. And probability of 2 successes and 1 failure this way would be the same. And this one would be also the same, but we have to switch these. But we still have 2 3/4 and 1 1/4. Now, notice that these 3 are the same, but they're not the same as this one or those, right? But those 3 are the same. So we just have to add them. And to add them, you just take 3 of these, right? So the question is now, how do we know how many different ways we can get certain number of successes? And that is the question that we're going to answer here quickly. People realize that how many different ways we can get, for example, 2 successes or 3 successes, turned out to be had to do with this. So here in algebra, people knew how to expand these. So what they did, they looked at these numbers right here, and they realized that these numbers are actually the numbers in the Pascal triangle, or Kayam-Pascal triangle. And those numbers are coefficients or these terms, see? So for example, If you raise s plus f to the second power, you get 1s squared, 1f squared, and then 2sf, right? So if you do it 2 times, you get 2 with 1 s in them, you get 1 with 2 f's, and then you get 1 with 2 s's. If you do it 3 times, you get 1 with 3 successes, 1 with 3 failures, 3 with 2 successes, and 3 with 1 success. So that's where these numbers come from. And then there has a formula. There's a formula that can actually give us those numbers, and that formula comes from counting. And the notation for it is this. So this would be number of combinations of n items taken r at a time, and that is has a formula, and that formula, which as I said we don't use, let's call this x instead of r. So the formula for that is, in the numerator is n factorial, and denominator is n minus x factorial, and then multiplied by x factorial. There. That's the formula to find those numbers. So people figured out how to find these numbers, and if you can find those numbers, then you can find the probabilities, right? If you do it 3 times and you want to find what's the probability that I'm going to get 2 successes, then we know there are 3 different ways you can get it, and each time is easy to calculate. So each time would be what? Well, each time would be this formula right here, right? So for example, if I want 2 successes, that would be probability of success to the second power, probability of failures to the first power, right, if I do it 3 times. And then how many different ways can I get this? This many. So, and this actually can be calculated with the calculator, so we don't have to go through all that n factorial and all that. So I'm going to show you how to do it with the calculator in a second. So as you see here, we can see that to find the x success, probability of x 0 success, we can do this. Probability of 1 success right here, probability of 2 successes, probability of 3 successes, right? So each of them would be a number, and we can do that with a calculator. Either using this formula directly, which we're not going to do, or using let me get this out of the way. There you go. So let's first figure out how whether we have a binomial situation or not. So the State Health Board is concerned about the amount of fruit available in school lunches. 48% of the schools in the state offer fruit in their lunches. So this implies that 52% do not. What would a success be in this case? Well, success is offering fruit in their lunch every day. A trainer is teaching a dolphin to do tricks. The probability that the dolphin successfully performs the trick is 35%, and probability that is not successful is 65%. Out of 20 attempts, you want to find the probability that the dolphin succeeds 12 times. State the probability question. Well, first of all, this situation is x. X is a variable, random variable here, and x is number of successes. How many successes can the dolphin have? Well, it can have 0, 1, 2, all the way to what? Could be all the way to 20 successes. And each of them has a probability. So this is a probability distribution which is binomial, because there is a probability of success, and we do it fixed number of times, and they're all independent every time the dolphin does it. So this is capital X. So probability that the capital X succeeds 12 times. So basically what we want to do is, if this is 12 here, what's the probability of 12 successes? So you see how difficult it is to make that table and count. That's just too much work. So instead, what do we do? Well, we use that formula. We say C, and then 20 and 12 here. That's 20. And then probability of success to the 12th power, and probability of failure to the 8th power. And that's it. We can calculate it. But in this case, we just had to state the probability, which is just that. We haven't got to calculating it yet. We're just practicing. A fair coin is flipped 15 times. Each flip is independent. What's the probability of getting more than 10 heads? So again, we have a situation where X is 0, 1, 2, all the way to 10. And probability of success is 0.5. And probability of failure would be 0.5. So the number of tries is 15. Oh, 15, not 5, not 10. Sorry, 15. Okay, state the probability question mathematically. It says, what is the probability of getting more than 10 heads? So we want to find probability that X is greater than 10. We're going to see how to do this in a second. But for now, what we want is this. See, here is the probability of, here are the values of X. Let's say we go all the way to 9, and then more than 10 here. Okay, 10, 11, and all the way to 15, right? So when we say probability that X is greater than 10, it means what? 10, 11, 12, 13, for all the way to 15, right? For every one of those, we're going to have a probability and add them all up, right? Now, to do this, we got to find each probability and add them. That's like many of them. So are we going to do that by hand? No. Calculator can do that for us, and we're going to see how in a second. All right, so notation for binomial is, we say that X has binomial distribution, and the parameters that we need are N and P. That's it. So here is an example. It has been stated that about 41% of adult workers have a high school diploma and they're not interested in further education. If 20 adult workers are randomly selected, find the probability that at most 12 of them have a high school diploma. So at most 12 means X has to be less than or equal to 12. So you see, you have to go to 12, right? In the table, we have to go to 12, right? And then 11, and then 10, and go all the way to 0, right? And then add them all up. Now that's difficult to do. There's a lot of work. So what we do instead, Instead, we're going to use a calculator. So calculator can find probability that X equals to X by doing binomial PDF, and then you put the N first, then you put the probability of success, and then you put the X. This is going to go to X and find that probability for you. So basically, calculator is going to put it in this formula, right? So it's going to put the N over here, it's going to put the X over here, it's going to put the P over here, and it's going to take 1 minus P and put it there for Q, and then gives you the answer. It's much easier to do it with a calculator. Also, we have another one, which is probability of X less than or equal to X. And calculator does that for you, and that is binomial CDF, NP, and X. So now the calculator is going to go, let's say this is your 0, 1, 2, all the way to X, and then all the way to N. So calculator is going to go to X, and the number before that, and the number before that, and all the way to 0, and add them all up for you, and give you the answer. Which is pretty good, because that takes forever to do. So for example, in this problem, we want to find probability that X is less than or equal to 12. We are going to use a calculator. So I'm going to go to second distribution here, and then go find binomial CDF. See, right there. CDF, not PDF, because it says less than or equal to. So I'm going to put N, which is what? N is, where was N? Did I get N? 20. Right. So 20, and then probability of success was 0.41, and X is 12. There, see, 0.97 something. In a matter of fraction of a second, you get the answer for us. So that's how we do it, by binomial CDF. Now, what if we wanted to find probability that there are only 12 successes? Then we would have to use binomial PDF. So to find the probability of only 12 successes, we go to, again, second distribution, and we go find binomial PDF right there. And then we put 20 again, comma 0.41, and comma 12. That is, of course, it's about 4%. So now, how do we find probability that there are some other options? For example, probability of X greater than 12. Well, notice that 0 is here, 1 is here, and it goes all the way to 11, and then goes to 12, and then goes all the way to 20, right? So greater than 12, not greater than or equal to, just greater than. What we have to do, we have to go to 12 and then 13 and all the way to 20 and add them all up. Well, that takes a long time, and the calculator doesn't have a way to do it directly. So what we can do is we can go to calculator and find from 0 to 11 and then subtract it from 1, because we know all of them add up to 1. Now, how do we find from 0 to 11? Well, we know how to do that. That's just what we just did. So we're going to, so the way we do this is by going to, get this out of the way. So probability that X is greater than 12 would be 1 minus binomial CDF, not PDF, binomial CDF, and then 20.41, and then 11 here. Now, I don't put 12, because if I put 12, it counts 12 as well. So it's going to go to 12 and then go backwards from 12 to 1 to 0. But I don't want that. I want it to go from 11 to 0, because I want to count 12 on this side. So this whole thing is 1, and I want to take that much away from it. So I have to put an 11 here. So with a combination of binomial PDF and CDF and a little bit of maneuvering, you can find all the answers here. And I have done it here for you. I could do it again on the calculator. So in order to do this problem with the calculator, we have to go to 1 minus, and then go to binomial CDF, and put 20, comma, 0.41, comma, 11. Right? Oh, my fault. So if I do probability of x greater than 12, I want 13, 14, and the rest of them. So I want for 12 to be included. Now what I discussed right now, that might have confused you a little bit. What I discussed was this one. What's the probability that x is greater than or equal to 12? That's what I discussed. But I was pointing at this one, is the new one. This one is already here. So probability that x is greater than or equal to 12 would be from 0 all the way to, let's say, 11, and then 12, and then 13, and all the way to 20. So greater than or equal to 12 means all of this, right? If I mean greater than or equal to 12. So I'm going to have to use 11, which I just discussed. But if I erase that, what happens is that now, let me do it. So now if I want probability of x greater than 12, so greater than 12 doesn't include 12. So it's 11, 12, 13, right? 14, and all the way to 20. So it doesn't include 12, so I have to include all that and then subtract that from it. So I'm going to have to put what? I have to put 12 in here, and you see it there. Sorry about that. I was trying to add another one besides the one that I already have here. So any of them, you see, probability of x equals to 12, probability of x less than or equal to 12, probability that x is greater than 12, and probability that x is greater than or equal to 12. You should be able to do either of these, right? So this one is just PDF, right? This one would be, if I less than or equal to 12, it just would be CDF. I don't need to have one or anything, right? So these two you could do directly, but these two, as I just discussed, this one greater than 12 is 1 minus CDF, and inside the CDF you want to put 12 there. Now this one is 1 minus CDF, and inside the CDF you want to put 11 because you want to add, you want to include 12. So that's how you do these. So now if you graph the probability distribution, you get a histogram, right? So obviously you get a histogram, and the histogram is going to look like that. Let me get rid of that. So it's going to look like this, the histogram, and it's going to have a mean, and it's going to have a standard deviation. So every distribution that we're going to talk about from now on has a mean and has a standard deviation. So I'm going to show you where it comes from, the mean and standard deviation of a binomial distribution. Then I'm going to go back and do some problems. So mathematically, that's where it comes from. The reason that we can't do it by the simple formula from chapter 2 is because there are a bunch of probabilities here you have to calculate, and it's a tedious process. So what we do, we use calculus to find the mean and the standard deviation, and then we get the formulas and we come back and use it in statistics. So here is the mean of a binomial distribution, and here is the standard deviation. So we're going to go back and let me see, here we go. So the mean of the distribution is NP, and the standard deviation is and the standard deviation is the square root of NPQ. So NP is mu, and the standard deviation is the square root of NPQ. So for example, if I roll a die and my success is to get 1, number 1, probability of success is 1 over 6. What if I do it 6 times? If I do it 6 times, if n is 6, and in the long run, if I keep rolling a die 6 times, in the long run, how many 1s should I expect to get when I do it 6 times? Well, in the long run, maybe you do it once and you get 1 1. Next time you do it, maybe you get 2. Maybe next time you do 3. Maybe next time you don't get any, right? And so forth. But in the long run, the average is going to be 6 times 1 over 6, which is 1. That means you should expect to get 1 1 every 6 times that you roll a die. Now, if the probability of success, let me give you another example. If the probability of success when we flip a coin is 1/2 to get heads, let's say. To get a head, you get the probability is 50%, 1/2. Now, if I do it 20 times, on average, how many heads can I get if I do it 20 times? Well, it would be 20 times 1/2, which is 10. All right, so it says about 32% of students participate in a community volunteer program outside of school. If 30 students are selected at random, find the probability that at most 14 of them participate in a community volunteer program. So here, at most means less than or equal to, and less than or equal to, we said, is binomial what? Binomial CDF, and then n is 30 in this case, probability of success is 0.32, and then comma 14. So it goes to this number and then goes backward all the way to 0 and then adds them all up. And that's what you get if you do that. All right, what's the probability distribution here? It says in 2013, Jerry's Artarama art supplies catalog. There are in it 560 pages. Out of those, 8 of them are pages that feature signature artists. So 8 out of 560, if you randomly open that book, the probability that you get a signature artist on the page is 8 out of 560. Now, if you randomly just go, here's the book, right? And then you go to the book, randomly, you go one time and you look at it, no, it's not signature artist. You close it, you go back again, do it, yes, it is. You go back again, you close it, you go back. So randomly you open some page, right? So if you do that 100 times, then X is the number of pages that you get, number of signature artists that you get, right? Now, is it possible that every time you go to the book 100 times on a row you get a signature artist? Well, probably not. That would be very small probability. So we can calculate. So X here is basically 0. X is 0 all the way to what? To 100. And then probability of success is that. So this is a binomial distribution, right? And n here is 100, and probability of success is 8 over 560. All right, so we talked about binomial distribution. We know what the mu is. We know what the standard deviation is. And if you square it, you get the variance, of course. Formula is this right here, but of course we don't use it because you have to use that. That's a lot of arithmetic and tediousness. So we just use binomial PDF and CDF. So again, I showed you where these come from. This is the calculus, and we don't have to know this. We just know the formulas. All right, so it says find the following probabilities. Find the probability that 2 pages feature signature artists. So we have the same situation. This is going to be binomial PDF, 100, 8 over 56, and 2. That's probability of exactly 2 pages. Probability that at most 6 pages feature, at most 6 means less than or equal to, that's a straightforward, that's binomial CDF. Now, probability that more than 3 pages, now more than 3, remember we have 0, 1, 2, 3, 4, all the way to 100. Now, more than 3 means 4 or more. So it's 1 minus that. But how do we get that? Well, that is binomial CDF right there. So that's that right here. Okay? So if you subtract that from 1, you get probability of x greater than 3. And it says, what is the mean of this? The mean would be 1.4. So that means if you keep going to this book 100 times, every time 100 times, right? And if you do it many, many times, what I mean by many, many times, that means today you go to it 100 times, and then tomorrow come back, you go to it 100 times. And then every time you go to it, you might get several pages, maybe 3 that have signature artist. Next time maybe you get 1, and so forth. If you add these numbers and divide by how many times you did it, the average is about 1.4. So you expect to get about 1.4 pages on average. Of course, you can have 1.4 pages. That's an average. The average is not real, but it gives us a measure of what to expect, right? All right, now I'm going to end this video here and do another one for the rest of the chapter. So we're going to call this chapter 3A. Chapter 4, chapter 4A. And that's what we're going to do. And I'm going to continue. So I see you, I'm going to see you in the next video, okay? It's going to be chapter 4B. All right, I'll see you in the next video.